Welcome. In this segment, we're going to discuss electrical and mechanical components. By the end, you should be able to identify the major photovoltaic components, including the photovoltaic panel, the inverter, the battery, and the charge controller. You should also be able to identify the balance of system components, mounting, wiring, and electrical protections, and identify the electrical code requirements. We're going to start with the photovoltaic module on the rooftop, then go to the inverter, and then eventually to the connections in the home. It begins at the photovoltaic module. This is something that we've discussed in previous lessons, but let's look at that photovoltaic panel itself. As a reminder, it's comprised of several photovoltaic cells which are wired together in series to produce the photovoltaic module. Multiple modules are wired together, typically in series, to produce a photovoltaic array. Now, what do we do with that full array? The electricity produced from the photovoltaic array is DC, or direct current, whereas most homes, buildings, and residences run on alternating current, or AC. An inverter is needed to convert the electricity produced by the photovoltaic array so it can be used in the buildings. The inverter is really the heart of the connection between the photovoltaic module and the building. There are several types of inverters that are available. Larger inverters can accept and convert photovoltaic electricity from about 10 to 80 modules. You can also have multiple smaller inverters in one large installation, serving only 5 to 10 modules per inverter. In all cases, you need some sort of monitoring system to both quantify the amount of electricity being produced and monitor the electrical grid connection. Monitoring the electrical grid maintains frequency parity and allows response to mandated shutoffs, like when there is no grid electricity present. These inverters are designed to handle multiple solar modules. There's also a newer option on the market called microinverters, which are designed to have a single panel connection, and out of that microinverter comes alternating current, or AC. That means that a single photovoltaic module's DC output is converted to alternating current and wired directly into the home. Microinverters also comply with something called rapid shutdown, because each panel is connected to one microinverter, which can then respond to changes in the grid, such as calls for shutdown when needed. This is an inherent safety associated with the microinverter because there's a relatively small voltage coming out of each panel. Microinverters are also compatible with small and uniquely designed systems. In the case of being off-grid, batteries may be required. Batteries are not a requirement if one is wired or connected to the grid, but they are necessary if one wants to work off-grid or requires a backup in the case of electrical failure. Battery banks are made of either sealed or flood-type cells of lead-acid batteries, though lithium-ion batteries are just starting to come onto the market. One code requirement for battery banks is that they have to be within 20 feet or about 3 meters of the inverter. So batteries are generally installed inside a basement space or a storage utility area where there's enough support for the weight of the battery as well as a close connection to the inverter. The one other piece that's needed with a battery system is a charge controller. The charge controller ensures that batteries are not undercharged or overcharged to prevent the risk of failure and/or fire. So the charge controller is an important piece and the brains of the operation between when the battery gets charged or discharged. The next piece of the electrical system is a building's electrical panel and the wiring infrastructure. Photovoltaics integrate with existing distribution systems, meaning that a photovoltaic electrical input is wired directly into the electrical main panel, along with the grid connection, or in this case, of off-grid wired alongside a generator. The breaker controlling the photovoltaic system is generally within the main electrical panel, so there's no need to rewire the electrical system. There are several electrical code requirements detailing how photovoltaic systems are electrically integrated safely into buildings. One of the important ones for planning purposes is that the sum of the main breaker and the photovoltaic breaker must be less than 120% or 1.2 times the rating of the electrical panel's bus bar. We'll go over this aspect as well as other electrical pieces in subsequent lessons on electrical requirements. Finally, the last piece for electrical consideration is the National Electric Code. The U.S. National Electric Code, or NEC, dictates the type and size of wiring that is required and allowable distances and conduit. Some municipalities use a separate electrical code from the NEC, and countries outside the United States will also have their own code requirements as well. According to the NEC, one requirement is that there are disconnects placed between the DC side of the photovoltaic system and the inverter, as well as a disconnect on the AC side of the system. That shutoff is typically part of the inverter itself. Electrical connections may use USE2 for outdoor use or PV photovoltaic wire for outdoor and sunlight ratings. These are defined within the NEC in the same way that typical indoor and outdoor wiring is already defined. There are strict grounding requirements stating that electrical systems are grounded, as well as the metal components of the photovoltaic system and the mounting system. All of these rules are defined in Article 690 of the National Electric Code, which specifically addresses solar installation considerations. Once all the electrical components are considered, a system diagram can be designed by a solar designer or an electrician. This is a 3-line diagram that shows where photovoltaic modules are wired to a disconnect, the disconnect to an inverter, and the inverter wired into another AC disconnect, and then wired to the main breaker, which then connects to the rest of the building components as well as the utility. Now that we looked at the electrical considerations, let's consider the mechanical components. The mechanical components are what connect the photovoltaic array to the building. There are several commercial manufacturers for these parts, but they all have some degree of compatibility. There are metal racks that connect the photovoltaic panels using specialized clips, and those metal racks are then attached to mounting points. Those mounting points are then connected to a rooftop using lag bolts or clamps. So first we connect the photovoltaic panel to the racks, and then the racks to the roof. All of the weight considerations need to be addressed by an engineer and/or architect before proceeding with installation. Waterproofing systems protect the roof and building from water penetration using rubber gaskets and sealed boots. The mount points are then lag bolted into rafters, thus connecting the system from rafter to module. In the case of a standing seam roof, a metal seam clamp attached to the rack and then to the roof prevents roof penetration. For flat roofs, one of the ways to be able to attach the panels is to use ballasting. Ballasting provides a weighted system, so roof penetration is not needed, and there's enough weight provided in the ballast system that prevents wind shear and the photovoltaic panels from lifting off of the roof. Again, this adds a fair amount of weight, and an engineer needs to be consulted to make sure the roof can support this kind of load. Ground-mounted systems are somewhat simpler to design and install because they are located on the ground and weight loading is typically not an issue. The mounting systems remain the same, but the racks are connected either to a single post that's connected to a single concrete footer, or a rack is constructed that's attached to concrete pads. Pole-mounted systems have the added advantage of being able to be tilted and turned, including compatibility with tracking systems. We'll discuss the advantages and technical aspects of tracking systems in a later lesson. So, in summary, you should be able to now identify the major photovoltaic system components, including the module, the inverter, the battery, and the charge controller. You should be able to identify the balance of system components like the mounting system, the wiring, and the electrical protections. You should also be able to reference Article 690 in the NEC that addresses solar photovoltaic code in the United States. In subsequent lessons, we'll be discussing the history and growth of photovoltaics.